The meeting.
All right, success. Okay, so we're ready to get going. We'll add the 5 minutes of uh, technical difficulties at the end. Okay, Dan, the floor is all yours.
Okay, so let me go back here. So this is joint work with Lona Smith, Gary Turness for some time, and much more progress since Juan Angong joined us. So again, it's not final results, but I'll tell you something about the process we've gone through. After general introduction, tell you what the issues are we're wrestling with. I'll talk about a particular class of games that has sparked our investigation, games of timing, and some very cute equilibrium predictions that we thought we'd see. We ran a pilot experiment a few years ago, and I'll tell you what happened there. It wasn't what we expected. We didn't get the Nash. We got something quite different, and that sort of made us pause. What we've been doing mainly in the last year or so are simulations, and I'll tell you what kind of results we got from those simulations. That's where I'll spend maybe half my time. Um, so for a proper talk for this audience, I should give you a lot of theoretical results, and we've really just changed our focus recently. And so I'll tell you about the kind of approaches we have in mind, but I won't give you any results. And that'll about do it. I'll sum up and hopefully get some of your thoughts, and maybe as we go along. All right, so by way of introduction, what we're interested in here are population games with their action space it's an interval, so continuous action space, and in model this is a continuum of players. There's a lot of important applications. The first one I encountered in my work was models of price dispersion in the spirit of Burdett and Judd. And later in my own work, I encountered this kind of game in thinking about conspicuous consumption modeling Veblen type dynamics, something I haven't done myself, but I think is widely used, or looking at models from distant location from urban center. But what I want to present today is what motivated this research. It's a very interesting class of games, not that well known, I think, or not as well known as it should be, which are games of timing, where both absolute and relative timing matter. Now, the reason I'm interested in presenting this to you and getting your results are that in a set of these games, a large set, that there's a sort of a unique. It might actually not technically be a unique Nash equilibrium, but a unique reasonable one after maybe a mild refinement. And that unique Nash equilibrium is dispersed. That is, its support includes an entire interval of the action space. Now, for a reasonable Nash equilibrium, the general presumption among applied economists and even most of you is that Nash equilibrium, it's a nice equilibrium, it's unique. It should predict the kind of behavior you'd see in situations that the model is supposed to represent. And I'm going to argue, and that's what we presumed when we started this project, but we've come to the view that this presumption seems to be wrong. I'm going to present a lot of evidence that the Nash equilibrium of this sort, I don't know if I want to say all of them, but typical Nash equilibrium of the sort I just described are dynamically unstable. In computer simulations, also in human subject laboratory experiments, the kind of process, the adaptive dynamics that we see, even if you start near this nice Nash equilibrium, this target Nash equilibrium, they tend to move away from it. And what the kind of process we're seeing, they don't seem to converge to some other behavioral distribution, some action distribution, and any particular action distribution. Instead, they seem to, the distribution seems to cycle in a particular way. So, and that seems largely independent of the initial distribution. So you can start in a lot of different places, end up going through pretty much exactly the same cycle. Now you can push that cycle around a bit as you change the game parameters or the adjustment procedure. But within at least a very broad class, you end up with a general sort of cycle that I'll try to describe in a little more detail. So we think we're dealing with limit cycles. In some ways, I hate to use the word Edgeworth cycle because it seems to mean much different things to different people. But in terms of the way Edgeworth described in his original book, it seems to be kind of like that. We, for whatever reason, have called them inchworm cycles, and maybe you'll see why. But I don't think that's a great name. Maybe you'll have some suggestions on better things to call them, and some thoughts on when they occur and when they don't. So that's my introduction, my general introduction. What I want to do now is describe a particular class of games of timing in normal form that our project is focused on. It's a pretty broad class. We think the phenomena is even broader than this broad class, but let me be specific enough to say, here's a class of games. So imagine a continuum of players, each one of them negligible in mass, and each chooses an action from the same interval of non-negative numbers, non-trivial interval of non-negative numbers. And their choices can be described through a cumulative distribution function, so which could be called a quantile function. And the point is, for this class of games, the payoff depends on both their actual choice. Think of this as the time at which they make the move, and also where they fit within the distribution. So I'm writing it here as a product of two factors, although most of the results that I'll show you later can be expressed more generally. But if you write it down as the product of these two, we can do some much cleaner. We can describe it parametrically and write down parametric descriptions, so on. So it's handy to write. Anyway, the point is that the payoff is impacted both by the fundamental action, that is, think of this as the time at which they move, x, and by where that falls within the distribution, whether they're early or late or in the middle. So an example of this is a war of attrition, where it's advantageous to move late. V would be increasing in Q. Or a preemption game in the opposite case, where it's advantageous to move early. First place I saw this kind of game described is called raiding the berry patch. The time X, there'll be the patch, if left alone, will have a maximal harvest at some particular time. If you come earlier or later, it won't be such a great patch. But on the other hand, if other people have got there and eaten up all the berries already, you won't do so well either. So it's a kind of a preemption game, right? This a broader class of games like this and broader is analyzed in an econometric paper a few years ago by Lona Smith and two other co-authors. And what I'll say in the next several slides is based mainly on that paper. Well, actually, I don't know if they do this parametric example in there. I don't know that they do that many parametric examples. Anyway, a simple example for the fundamental factor, right, that depends on the directly on the timing is just hump-shaped, lambda a positive number, and just staring at that, you can see that this factor is maximized at what we'll call the harvest time, lambda. For examples I'll do, we'll actually just set lambda equal 10 and not mess around with it. I mean, that's just sort of can set the scale and everything else. So it's not that, it's important that it have a hump shape, but it's not so important to move this parameter around. It's the other parameters are going to be more important. So let's look at the quantile factor, which is your relative to position. How does your relative position matter? We're going to, again, use a quadratic that can be hump-shaped there for certain parameter values. In particular, if rho, it's not too hard to see. It takes a little bit of algebra. Then if rho is, if gamma is between rho and rho plus 2, we do have an interior peak at some point in between 0 and 1, at some quantile in between 0 and 1. If we're outside of that, on one side, we have a monotonic decreasing function here. So that would be a preemption type game. And on the other side, we have a war of attrition type of quantile factor. The most interesting predictions arise from the hump shape factors in this region, in this interval. Let me explain those after I say what's Nash equilibrium. Of course, in this situation can be thought of as just the distribution function, right, or the quantile function. And it's a Nash equilibrium if supported only on points that that maximize the payoff. Okay, it's just standard and slightly odd way of expressing the usual Nash concept. Now, as a distribution function, CDF, they can have jump discontinuities, and the term that the Lonis and his co-authors coined for that is a rush, a jump discontinuity, meaning a bunch of some positive fraction of the population is moving at exactly the same time, choosing exactly the same X. And slow play is where there's a positive density. So, yeah, the number of people moving in some particular time interval is proportional to, up to first order is proportional to the length of that time interval for a small time interval. All right, so the support has those two kinds of pieces of it. Turns out there are some uninteresting Nash equilibria that are fragile. And there's a nice little, I won't write down precisely what it is, but a nice little refinement to get rid of them. Basically, a sort of tremble either to slightly later time or to a slightly earlier time, get the same results. And in that paper by Lonis and co-authors refers to those nice equilibrium as safe equilibria. There's actually 5 subcases depending on how the parameter gamma falls relative to the parameter rho for the quantile function. Remember, those are the 2 parameters for the quantile function. This case, it's not hump shaped, and you get a pure preemption game. In this case, again, it's not hump shaped. You get a pure war of attrition. But there's subcases in the interval of interest. In particular, in the central part, you can actually get both kinds of equilibria. Let me show you some diagrams to describe them. So there's a unique safe equilibrium if we're in this, if gamma, the parameter gamma is in this region, and it's there'll be a rush, a bunch of people moving early, then gradual play up to harvest time. In this region, though, we have both kinds of equilibria. I mean, we can have a rush either early or late. And these figures are supposed to suggest the size and the location of the rush. The size by how big is the circle, and the location by where it's centered. And so anyway, we have all these different possibilities. Yeah, what I want to do now is actually show you specific examples. So we have in this parametric example, remember lambda is the optimal harvest time, and gamma and rho are these shape parameters for the quantile function. So in this case here, there's actually no rush. It's just a normal sort of preemption game. And here's what the equilibria look like. And the cumulative distribution function is shown here in orange. So you can see that the density, the slope of this, or the density for this Nash equilibrium is high at the far end of the support, which is around 5. It's not exactly 5. It's a little. Here's what we can say about the Nash and the rush time. That is the support interval is just below 5 up to 10. And there's a rush of size 0. In other words, no actual rush is the borderline case at the lower end point, Nash equilibrium, 7.5. Okay, so back to this figure I was showing you. That's the Nash equilibrium distribution. And in payoff space, um, we have on the support, everybody is getting the same payoff. We get the equal payoff property, and lower elsewhere, right? That makes it a Nash. Now in light blue here, I've shown a discrete approximation, which we're gonna for an experiment with. We can't do a continuum of players if we can't get that many human subjects in a room. And for simulations too, we're going to do, a discrete approximation. So I'm showing you here a good sort of a closest discrete approximation with 20 players. And so you get some jaggedness in the payoff function, but with this nice approximation, they're all maximizing at the locations we given them at these discrete locations. Okay, is that all clear? So that's an example of a Nash equilibrium. Here's one that's a little more, even more interesting, although it looks similar, where I just changed the parameter and moved it into that region where we have a rush. Oh, I guess I should have pointed out what that rush is. At the 3/8 of the players are all going to move at once at the lower end point of the support interval, and then the remaining 5/8 of the players come in gradually over the rest of the support interval. And so again, this figure looks pretty much similar to the others. This looks similar, except there's an actual jump discontinuity right up to 3.75. Anyway, that's the Nash equilibrium there. Here we are for the next one in order. Well, I guess I should go back. The next parameter values, we actually are in the region where we have two Nash equilibria. One with in this one, there's a huge early rush. 3/4 of the people all move in at this time, and then there's a slow play over this shorter interval, and a payoff of 108 for exactly the same payoff payoff parameters. There's also a different equilibrium with a large late rush after the harvest time, after 10. In other words, at the far end of the support interval. So here's the I think I clicked the wrong one there. Here's the early rush. Again, similar to what we were looking at earlier, but just, a lot of people moving in at once, 3/4 of them moving in at the very first moment in the support, and then the others moving in gradually. And then with exactly the same parameters, we have this other equilibrium where nobody moves early, and then they start to trickle in faster and faster, and then there's a big jump, all of them moving at once right at the end of the support interval. So that's
Just to understand the graph here, the payoffs seem to be higher than the Nash equilibrium payoffs. Is this correct? The left-hand diagram?
here.
Yeah, there are these.
Oh yeah, that's right. It was discrete approximation. We put these here. This the red here is the payoff at. Oh yeah, yeah. That's a funny little diagram. I don't know if you should take it too seriously. The red line is at the continuum of agents, Nash equilibrium, and then the way those dots are shown, they probably actually should be. The dots should appear at these little peaks, and the continuum approximation gives us payoffs that are a tiny bit higher. I mean, the discrete approximation gives us payoffs that are a tiny bit higher than in the continuum.
I see.
Is that
I see. Thank you.
responsive to your question?
I think so. Yeah.
Then, symmetrically, we have this case where there's, oh, how did we get that? Oh, I think I jumped to the wrong place. not quite sure how that happened.
I think you were at like page 11, 12.
Yeah, okay. This is where we are. I'm going to try it one more time. Maybe I shouldn't. Yeah, these figures are similar. I'll just go to this last one here. So this is a case where there's no rush or we just miss a rush. And there's gradual play starting at harvest time. It picks up speed and then it stops at 14 for this particular set of parameters. Okay, so that's a striking set of predictions. And so this project began by saying, well, why don't we take this to the lab? I mean, the first thing was to get these nice parametric examples we could take to the lab and figure out on that. So anyway, we constructed software and we wanted to know the kind of questions we initially had in mind in this project is, well, could we actually get these rushes, where everybody's moving at the same time and, about the right number of people, right fraction of people and about the right time. And especially what would happen in the cases where you had multiple Nash, could you converge to either one or both of them? Would it depend on initial conditions? What would go on? So we developed software to run this for, it would seem to be good. We could maybe do more, but we aim to have it so it would work for at least up to 20 players. To give you some idea of what the software is like, here's an example with just 4 players, just for demonstration purposes. So this is in real time or, asynchronously. Each player is looking at a screen like this. Actually, this is a prototype. We had a slightly more refined version of it. But the basic idea is that right here, there's a slider. And by clicking a point like here, whoops. I shouldn't click on this screen. It's not going to do things I don't want. If a player clicks like this point right here, their position, which is shown in green here, will jump, so they can drag and click or just click and whenever they want and change their position. So here's the optimal harvest time. They're a little bit late here. And they have over the 3-minute period or whatever, we can just pick the length of it. I think 3 minutes is typically what we did. All the players can move around whenever they want. That will change the quantiles and, of course, change their absolute position. And we apply the payoff function and show the payoff function, I call this the landscape. Given what the other players are doing, this is what the payoff function will look like for the given player. And they can move around freely. Then they can see here what they've done historically. This is going over time. This sweeps out more and more. Green is their own action. And in this case, the other players have just been sitting there. They haven't moved yet. And this green area shows the accumulated payoff so far. Okay, so that's what the user interface looked like. We ran an experiment like that and thinking maybe we would converge to these interesting Nash equilibrium I showed you. But we didn't. Here's an example, one of the few I could find in our, we didn't save the data that well, but this is not atypical of what happens. So this is over time, and each player has their own color. So it looks like there's about a dozen players in this example that initially start out quite dispersed. I mean, quite even, well, randomly distributed between 1 and 18, 17, 18. The optimal harvest time in this is 10, just like in the examples I was showing you. Don't recall the parameter values, but it was a hump shape kind of thing. So we were expecting to see a rush, or at least a slow playing rush with a support interval between 10 and something. I don't know, maybe 5 or 6. Well, people did kind of move into that support interval and actually to a tighter one at this point. But then they started preempting each other. You know, there's some at any moment in time here, there's some distribution of behavior that's going. In this case, it's going from about here about 6 to 8. But then some people jump down to lower numbers and others follow. And so over this time, people moving down until they're all the way down to like, 1 to 3 or so around here. And then the red one, this player marked in red, jumps up to 10. Other players follow. In fact, they all follow within the next few seconds, 10 or 15 seconds, 10 seconds or so. And we're back up here, and they kind of are preempting each other, moving down to lower and lower locations, and then they jump up again, and they go through these kind of cycles, about 10 of them, I think it's a 3-minute time period. So that's one example, and we found quite generally with the human subjects, we could get to convergence to Nash equilibrium. Was a pure Nash equilibrium, like if everybody wants to move at 0, we pick parameters outside the range I showed you. So everyone wants to move at like 0. Well, we get approximate convergence to that. But games with dispersed Nash equilibrium, where there's some non-trivial support interval, we generally did not, we actually never saw a convergence of something that looked like a Nash equilibrium distribution on that short interval. We generally saw cycles where the choices begin to clump tightly, and the clump stretches a bit away from the harvest time, the tail catches up with the head, and then it repeats, keeps on edging down until the payoff falls too much, and then they jump back up or to the harvest time, and then resume that downward march, or in some cases upward march. I'll show you some other examples to show these cases. We tried a bunch of things, although it's slow and awkward to do so. We tried, different numbers of players and these discrete action, the discrete time versus continuous time, varied how much they could see about what the others were doing. We didn't do it exhaustively because it's slow and rushed, but we never saw convergence to the dispersed Nash equilibrium. We decided to.
Can I ask a clarification question?
Please.
Those iterations, so at every single point in time when you ask people to make choices, so it's a simultaneous move game, so you have to.
No. Well, I mean the static game is simultaneous move, but the way we did it in the experiment, it's asynchronous. They can each move at any time they chose within that 3 minutes.
And then immediately the picture adapts and to the choices that people have made earlier, or what?
Yeah. Well, there's a
Okay.
a little latency, but it's not perceptible. It's on the order of 50 milliseconds.
Okay, so it's not actually a simultaneous move game in that sense that when you make your choices, you can consider the other people's choices fixed for the moment. I mean, how do you pay this out then in the end? So
how do you pay them?
Yeah, how do you pay them?
Well, let me go back to that. Right. So at any moment in time like this, well, in the picture that you see here, these locations by these 4 players, including the given player, that's not changed over a certain time interval right here. So they're getting a flow payoff over that, and so the area is accumulating at something. This height is the rate at which their payoff is accumulating. Now this player is actually set up to jump here, and if no one else moves, they get a height here. So at that point, this payoff would jump to this height, and it would accumulate until somebody else moves. Maybe they don't move, but someone else moves it in a way that affects their payoff. Then there would, so it's piecewise constant, with jumps every time anybody moves. Is that?
Okay, thanks. Yeah, so essentially it's a large player repeated game in some sense, or long run game in some sense, right?
Well, so our thinking is that the static equilibrium would be predictive of where people would end up. They'd settle down to some kind of distribution that looked like that.
Okay, thank you.
And that was really what, Arthur?
Sorry. There may be equilibria of the asynchronous game that are quite different, though, right? That's what you it seems.
Oh, if the thing is a dynamic game, that would be a very complicated game to think of.
Yes,
But
yes.
we're thinking of that maybe the equilibrium of the. I mean, it's a presumption generally in the world, right? I mean, there's nothing in the world. If you have a static Nash equilibrium and you want to say something about the world, well, the world isn't static. People can move. If you'd like to think that it's predictive of a situation after things settle down, right? Even though people can move, no one will find it in their interest to do so. And what you'll observe, maybe after some uh, transitory period of adjustment, that you'll get a distribution that looks like Nash, and that does actually work quite well in many settings. But I guess the theme of my talk is that there's a bunch of settings where it doesn't. So we're not looking at equilibria of this asynchronous game of timing. We're thinking that these may settle down to a static Nash. Does that clarify what we're doing here, what we're trying to do?
I mean, the one interesting thing. Oh, sorry, Arthur.
I just told you that they didn't, but that was our presumption going in.
I mean, it would be interesting to see if, let's say, actually what they end up playing is an equilibrium of the asynchronous game. In that sense, then it would be an explanation. Yeah.
So someone raised their hand.
Yes, sorry, it was me. Do the individual steps that players are taking look like best responses here? Are they instantaneous best responses?
Well, in the simulations, we're going to assume that they're noisy, instantaneous best responses. Players can do whatever they want, but a very common thing to do is to look at where the peak is. So in this, can you see my cursor? So jumping to right here or possibly to right here would be a pretty common thing for people to do. And then when the landscape morphs a bit, so there are a lot of them that'll just chase the peak. And in fact, that's sort of what our simulations are going to assume. Uh, anyway, human being, they can do whatever they want, and they can, try to be forward looking and say, all right, I think I know where things are going, and I'm going to settle there ahead of time. I know what's going to be good ahead of time. Or they could be, always behind the eight ball, or they could, just decide I'm not going to move. And humans can do a lot of different things. But as we tried this experiment, we couldn't find situations where they were settling into something that looked like the dispersed Nash. We either got sort of trivial behavior. Well, in the case of a non-dispersed Nash, we did get nice convergence to that generally. But what we often got is these kind of cycles, and we thought it has something to do with people typically jumping to the current peak. So we wanted to simulate, what we thought adaptive dynamics that might resemble what people do. So what I want to do in this next part of the talk is describe our simulations. So Wyman has now a very flexible simulator written in Python. Is based on an earlier prototype, but allows us a lot of flexibility. You can specify pretty much any number of bots you want. We're typically we want something that's kind of a large number, but still finite. And we've looked at numbers. Well, I'll tell you more later about, but I'll show you examples for n equals 20, but we've gone much larger than that, up to 200 and occasionally more. We haven't tried to explore it with low n because we're interested in the continuum, Nash equilibrium approximation of actual behavior. So the user specifies how many bots they want and how they're initially located. Specifies, of course, the game parameters, and we're using the parameterization I showed you earlier. So there's these three parameters. We're going to keep lambdas at 10 in everything I show you, but vary gamma and rho. And then there's adaptation parameters. How many periods in each period? This is going to be discrete time in the simulation. Doing simulations that are asynchronous is more. It seems more trouble than it's worth. Although there is some variations that do that. So, but the main simulation, the basic one, is in discrete time, and we allow some user-specified fraction of players to move in each time period. Could be one, but we're typically going to do like 5 or 10%. And then we need trembles both because of the equilibrium notion and just to avoid trivialities. So we're going to compute on a pretty fine X grid. Each time period, we're going to do the following computations. What's the payoff landscape at the grid point? What is the payoff value given the distribution of behavior in the previous period? All right, given that quantile function, what's the payoff at each point? What's its maximum over the landscape, and where is that? Possibly not unique. Then what would be unique then is the regret for given what the player actually was doing compared to what they could have done given that distribution last period. How much is the shortfall? And those computations provide what we'll call a leaving function, which players are chosen to move. We want a total of G n of them for this fraction, say 5% of 100 players or 5 players to move. Depending on the parameters you have, it might be a lot more. It might be 20% of 1,000 or whatever. There's a certain number of players to move, and what we do is choose them in proportion to the proportion of their regret. So the greater their regret, the greater their shortfall, payoff shortfall from the optimum, the more likely they are to move. And in our basic simulation, we're going to do variations, but that's what we do that's who gets to move and where do they go? Well, in this basic simulation, we just point them at the highest payoff point, the argmax, with a little bit of tremble. And again, as I said, that's to avoid trivialities, and is also consistent with the equilibrium refinement that's called safe equilibrium. All right, so here's a picture I really wanted to see, want you to see of the dynamics in motion. Oops, how did we? This isn't where it started. Like I was. Let me try this again. I unfortunately didn't start it at the right. Oh, whoops. I'm sorry. Missed again. Well, I guess will this work? Yeah. Okay, here's period 0. We initialize this simulation with one of those I showed you before. This is an early rush. There's a lot of people come in at this first time, which I think is just under 0.5, and then they taper off until they're all in at 10. So it's a no rush. No technically speaking, no rush. This is the equilibrium distribution. Okay. And so we're going to start them off at a discrete approximation of the equilibrium distribution. I think it's, again, this simulation has 20 players. So let me run it. This is by period 3. We have some people moving we have a bunch of different things as people start to move. We've moved some fraction of them, others we haven't moved. And you can see that it immediately is breaking up. It's not like it's hanging at the Nash. It's already moving away from the Nash. And then by period 10, we have a substantial fraction. It looks like more than 10, maybe a dozen of the 20 players are near the or a little bit below the optimal harvest time. So the CDF, right, it shows a few people low, then, not so many people in between. And then it looks like about half playing 10 or just below. That's already by period 10. And you can see that the number of people playing just a little below 10 is increasing as we go. And now by period 20, we have a clump that's noticeably below 10 and not very wide. And they're getting higher payoffs, by the way, than they get in Nash. Okay, let me just let the thing run now. Well, let me stop it now. So you saw that what's happening is that there's a clump and it's all moving down, right? They're preempting. This is similar to what we saw humans do in the experiment. We're seeing this in the simulation. There's one period of, oh, I'm moving the wrong way. It's moving forward in time. It's slowly working down. Let me let it run faster. So there you have our inchworm is moving at in this animation at a pretty high rate of speed. So period 143 of the simulation, most of the people here in the neighborhood of 6, which is pretty far down in the support of the Nash equilibrium, continuum Nash equilibrium distribution. Notice though, as we move along, the height of this peak is getting lower and lower, and nobody's here, but that U part of the function, the fundamental factor, is hanging in there. Okay, let me continue simulation. So right about here, this peak is actually right at the long run Nash, and it's not far above this. So if we run it a little further, it's not, and people are trying to switch to where their payoff is maximized, instead of preempting a little more, they're going to want to be here. And let's see what the simulation does. Let me back up a second. So right here is there's basically a tie, and then I move ahead one from period 206 to 207, somebody jumped, and that's affected the shape of the landscape. Period 208, 209, 210, 211, 212, most of them are jumping now. And in this simulation, by period 218, there's one laggard here, but they're pretty much all near the optimal harvest time. And I'll just let it run from here. And they're moving on down. So in this simulation, we're getting these same kind of things that we've been calling inchworm dynamics. And then, whoops, and that's it. Then now it just, this GIF file is going to start over again from the beginning. All right. Let me show you, this is the opposite parameter where we're going to have in Nash equilibrium, the support is from harvest time to later times instead of earlier times. And this is the one where there's an increasing density, but not quite a rush on the support interval 10 to 14. So we've lined up players and in a discrete approximation, I think it's 20 players again, and starting them off there. Okay, so and even after one period, it's breaking up. Here's period 6. It's definitely broken up, and some of them are getting, above Nash equilibrium payoffs. Let me just let it run now. So simulation, you're seeing it's inchworm dynamics, but it's going up instead of down, and that when the peak of this payoff at the clump falls below the payoff at the optimal harvest time, there's a jump backwards. All right, and so that's the cycle. So we've completed 2 cycles, and we're about to complete a third. Boom, that's the third. We're going into a fourth. and well, I could just about complete a fourth in the 400 or 500 periods that we've got here. In the cases where here's a case where there's supposed to be a rush, and the behavior is very similar, although it's a little slower here. So it takes 1,000 periods to complete 5 cycles in this case. I better speed up my presentation here. This figure is, you kind of notice this is just looking at the payoff as a function of location, averaged over time. And one of the things that's interesting about it is you can see that typically they're getting higher payoffs, not always, but typically getting higher payoffs than they would in the continuum Nash equilibrium. So until recently, what we were trying to do is find dynamics, plausible dynamics that would give us convergence to this continuum Nash. We tried a lot of different things, of course, different initial conditions, but that seemed to have very little impact, except for the first few periods in the simulation. We messed around with a leaving function so that it wasn't so sensitive to regret, or was more sensitive to regret. This only seemed to affect this frequency or speed of the cycle, but nothing else, or nothing much else, at least up to first order. We also looked at different arrival functions, such as a logit kind of distribution, where people might not necessarily go to the max. If they're not at all responsive to the landscape height, things break down. But if they're at least a little bit responsive to, they're more apt to go to a place to high payoff than to low payoff. We get cycles, although the less they become more ragged as the place that people jump to is noisier. We spent a lot of time on purification ideas, thinking that with this mixed Nash, making it. I don't know if I've got time. How I'm supposed to wind up in about 10 minutes. Well, I guess I started late.
It also depends on how much time you want for the discussion.
Yeah, well, I do want time for discussion.
So, but the slot ends at 6:20, accounting for the 5 minutes of technical difficulties at the beginning. And that is supposed to include our discussions.
So about 20 more minutes, including the discussion.
28 by my count.
28 minutes, oh, including the discussion. Okay. Well, I got a little time to say something about purification, and if you're interested, I can tell you more. One purification idea is that people see absolute time a little bit differently. So some people are on a little faster clock and others on a little slower clock. The impact was not that exciting. It sort of shifted the range over which the inchworm went a little bit, but not in a very interesting way. Another purification is not in terms of time, but in terms of quantile. That some people the purification works where your payoff as if your quantile is a little earlier or a little later than it really is, and got very similar impact there. Again, didn't really affect. We still were getting what we're calling inchworm cycles. Purification version 3 is that you get a payoff bonus for being near your initial Nash location. If that's a really small bonus, it seems to have no impact at all. For moderate sized bonus, the cycle takes a while to kick in, but once it does, it recurs. I'm sorry for the misspelling. For a large enough D, though, the Nash equilibrium distribution becomes a local attractor, and if you start not too far away from it, you fall into Nash. But as one of my co-authors says, that's cheating. We've changed the payoff function so that people just want to be in a particular place, and if they want to enough, then that'll rule. I was a little surprised. It didn't take quite as much as I thought to get people to stick, but anyway, we did manage. So we found something that got convergence to Nash, but it was pretty heavy, pretty strong medicine to make that happen. We looked at a bunch of other things, such as replicator dynamics are not really originally written for a continuum of continuous action set. So we looked at specifications that to us made sense to extend replicator dynamics to that. And the impact is, maybe I'll show you this one. You get kind of an inchworm that's running off the direction you want, but it doesn't stop. Here's a case where there's an inchworm down here, and with the usual inchworm dynamics, you'd expect it to jump up to this high payoff. But with replicator dynamics, if there's nobody to imitate up here, no one does that. So it's just sticking, in the neighborhood of its support, and it just runs on off. On the other hand, if you have enough players and enough inertia in there, so at least a few players there, then it will jump back, although slowly. So that's replicator dynamics. We did some payoff sampling. Instead of scanning the entire landscape, each bot is monitoring some subset of peers, and we combine that with all kinds of other things. So we did a lot of simulations like that, and they didn't seem to do a whole lot. They tended to slow down the inchworm, and when there's very little monitor going on, you're only looking at very few of them, then things can stagnate. But other than that, no, this doesn't really seem, for reasonable versions of payoff sampling, it doesn't seem to get rid of the inchworm. Again, it seems to be the attractor. We tried various kinds of payoff smoothing longer ago, and my recollection is that it tended to spread out the inchworm's support a little bit, but that's about it. All right, so the last part of my talk are some what I'm calling theoretical musings. We're starting now to try to develop some formal theory, and you all might have some thoughts on how best to do this. We've changed our approach. Instead of looking for ways to get to specify adaptive dynamics that converge to Nash, we're saying, all right, it looks like that's not not really an interesting attractor. We try to understand better why it's unstable. And well, I'll explain exactly what we're trying to do theoretically here. But before I do, there's maybe some words I'll want to use and just that I should say kind of what I mean. So dispersed Nash equilibrium, I think I already mentioned, just a Nash equilibrium whose support includes a non-trivial interval. And by clump, I don't know, I guess it's a relative thing, but there's some relatively short interval that contains a disproportionate mass. I think an important qualification to what I want to say in general is that it could be upset by strong local congestion effects. What do I mean by that? I don't want to define it too carefully, but basically that if you change the population density or mass, I mean, it could be some atoms too. If you increase the population mass in a neighborhood of a point, that tends to lower the payoff. So that's local congestion effects, which I think are an exception to what I want to say in general. Now about adaptive dynamics, they can be local or non-local. In terms of our leaving function and arrival function, if the arrival at a particular point depends on how many people are leaving in that neighborhood, either positively or negatively, then they'd be kind of local. But non-local is that, think of the way the dynamics work is that the leavers go into a pool, doesn't matter where they came from in terms of where they're going to end up. So the arrival function in that sense is independent of the leaving function in that local sense. A counterexample, something I played around with, as some of you may know, or gradient dynamics. Gradient dynamics are local. And the replicator function, as it turned out, is somewhat local. Well, not exactly, but effectively it is. Anyway, and then the last thing is payoff responsive, in that, maybe it doesn't move, that the arrival isn't always to a small neighborhood of the maximum, but at least it's responsive, and you're more apt to get people moving to a point the higher is its payoff in the landscape. Okay, so with those distinctions in mind, we're now trying to prove some version of the following two conjectures. Instead of trying to find ways to get convergence to the Nash, we're going to say we want to prove that actually it's dynamically unstable. If we have payoff responsive adaptive dynamics, we believe that's enough. Maybe other conditions are needed, but this dispersed Nash equilibria are unstable under broad classes of adaptive dynamics. So it was a fool's errand that we were on originally. That's what we now think. And that absent strong local congestion effects, we're going to converge to a limit cycle of a sort that is what I showed you. From a wide set of initial conditions, there's going to be some big basin of attraction, not to a point in the space of distributions, but to a cycle in this space of distributions. That's our conjecture. We think of this maybe going through three different formal results, and here's a semi-formalization of it. The first is clumps, that things tend to clump. If we have payoff responsive adaptive dynamics, arrivals will tend to be in a small interval, will tend to clump, and a disproportionate mass of the arrival will be to in relatively small regions or clumps. This could be upset by strong local congestion effects. I mean, you can get clumps at first, but they would be self-limiting with strong local congestion effects. Without those, we think the clumps become more and more massive, and that's a source of instability in the dispersed Nash equilibrium. That's our first, in terms of proving something, that's the first thing, is that kind of instability result. Then for some particular class of games, well, I'm not sure quite how general this is, but certainly it covers all the timing games that we've looked at. And I saw similar things to this in some price dispersion models. Once, though, we have enough clump in one or maybe a few clumps, there's a tendency of that clump to drift left or right, depending on whether preemption or postemption is the stronger force. There may be some class of games where this doesn't happen, but at least I think for a broad class, certainly including what we have, I expect to see this phase 2. And then phase 3 is when it's moved sufficiently far, there's some distant higher point on a payoff landscape. This isn't going to work for replicator dynamics, but given ones that are payoff responsive, in this sense that I had there, we expect there to be this jump or tunneling back to that higher point. And then we're back in the situation described earlier. And so if all three of these happen, then we have what we've been calling inchworm dynamics. Okay, so let me wrap up my presentation and hopefully turn it over to general discussion. We started with a presumption that a nice dispersed Nash equilibrium would eventually describe behavior, but after some human subjects experiments and some simulations, we've come to the view that, I don't know what the right name were, but these cycles of the sort I described to you, that they're actually ubiquitous, not ubiquitous, a little strong, very widespread. There's just a lot of situations where these kind of cycles is what behavior should converge to. Most game theorists, I think, would resist this. People in this audience might be among the exceptions. But anyway, we're not aware of any theory that we can apply directly to this situation. And the next step, at least for some members of the team, is to try to get some formal results of the character that I described just in the last few minutes. I'm very happy for this opportunity to present to the learning, evolution, and games community, because I think you're especially well placed to shed further theoretical and empirical light on these questions. So thanks very much, and I want to turn the rest of the time over to questions and comments.
Thank you very much, Dan, for a fantastic talk. I'll stop the recording and then we'll turn to the discussion.